Welcome to the AZ-900 Azure Fundamentals revision session. In this lesson, we're going to quickly set expectations for the exam and then build a clear roadmap in your head for everything that follows. The AZ-900 certification is designed for people at the foundation level. You don't need to be a cloud engineer or developer. It's aimed at students, career changers, people in business or sales roles, and technical folks who want a strong conceptual understanding of Azure. The exam itself is multiple choice, drag and drop, and short scenario questions. You'll often see things like, which Azure service fits this requirement? Or, is this IaaS, PaaS, or SaaS? So, our focus in this course is on understanding concepts, not memorizing portal clicks. You typically get about an hour for the exam, with a passing score of around 700 out of 1,000. Don't obsess over the exact cutoff. Treat it as a signal that you're comfortable with the fundamentals of cloud concepts, Azure services, security, and management. For preparation, the best mix is the official Microsoft Learn path, a concise set of notes or slides like these, and practice questions so you get used to the wording and style. As we go through, keep asking yourself, could I explain this in my own words? If the answer is yes for most topics, you're in a very good place. Before we continue, if you're finding this helpful, please hit the like button, share this video with anyone preparing for the AZ-900, and subscribe to the channel. And here's something exciting. If this video reaches 2,000 likes, we'll create an entire playlist course covering every topic in even more detail. Your support really helps us create more comprehensive content for the community. In the next slide, we'll start from the absolute foundation and answer the key question. What exactly is cloud computing, and how is it different from traditional on-premise IT? On this slide, we'll answer the simplest but most important question. What is cloud computing? At a high level, cloud computing means delivering computing services over the internet on demand. Those services include things like servers, storage, databases, networking, analytics, and AI. Instead of buying and owning physical hardware, your organization rents resources from a cloud provider such as Microsoft Azure. The key idea is that resources are available when you need them, and you can provision them yourself using the Azure portal, the command line, or APIs. This is called on-demand self-service. You don't have to wait for someone to rack a server in a data center. Another important aspect is broad network access. Cloud services are accessible over the internet from many types of devices, laptops, phones, tablets, or even IoT devices. A useful analogy is electricity. You don't build your own power plant at home, you plug into the grid and pay for the electricity you use. Cloud computing applies that same idea to computing. You plug into Azure and pay only for the compute, storage, or services you consume. This change from owning hardware to consuming services is what separates modern cloud from the old on-prem model. In the next slide, we'll go a level deeper and look at the essential characteristics that make something truly cloud according to widely accepted definitions. Now that we've defined cloud computing at a high level, let's look at the core characteristics that define a true cloud environment. First, on-demand self-service. You can create and manage resources like virtual machines or storage accounts without needing human approval on the provider side. You just go into the portal or use a script. Second, broad network access. Services are available over the network and are accessed through standard mechanisms, typically HTTPS. This means phones, laptops, and other devices can all reach them. Third, resource pooling. The provider runs large pools of compute, storage, and networking resources. These are shared across many customers in a multi-tenant model, with logical isolation so customers can't see each other's data. Fourth, rapid elasticity. Resources can scale up and down quickly, sometimes automatically. If your app suddenly gets more traffic, Azure can add capacity. When traffic drops, it can reduce resources again. Fifth, measured service. Usage is monitored, controlled, and reported. This is what makes pay-as-you-go billing possible. You can easily see exactly what you're using and what it costs. Together, these characteristics explain why cloud is so flexible and cost-efficient compared to owning fixed hardware. Next, we'll look at a subtle but very exam-important question. If Azure is running the infrastructure, who is responsible for security and management? That's the shared responsibility model. On this slide, we'll tackle the shared responsibility model, which shows who does what in the cloud. In traditional on-premise environments, your organization is responsible for almost everything, from the physical building and servers to the operating systems, apps, and data. In the cloud, this changes. Azure takes responsibility for parts of the stack, and you remain responsible for the rest. Azure is responsible for securing the physical data centers, the network, and the underlying host infrastructure. It also manages many aspects of the platform for PaaS and SaaS services. You, as the customer, are responsible for data, identities, access, and configuration. That means user accounts, permissions, application code, and security settings are still your job. The split depends on the service model. With IaaS, Infrastructure as a Service, you manage the OS, patches, middleware, and apps. With PaaS, Platform as a Service, Azure manages the OS and runtime. You focus mainly on the application and data. With SaaS, Software as a Service, Azure manages nearly everything. You mostly manage users, licenses, and data. A good mental shortcut is Azure secures of the cloud, data centers, infrastructure, and you secure in the cloud, your workloads. In exam questions, always look for hints like virtual machine you patch yourself, IaaS, versus managed database, PaaS. This tells you who is responsible in that scenario. Next, we'll shift from who is responsible to where workloads live by exploring the main cloud deployment models. Now that we've covered responsibility, let's talk about deployment models, essentially where your infrastructure and services live. There are three primary models to remember for the AZ-900. First, the public cloud. Here, infrastructure is owned and operated by the provider, like Microsoft. Multiple customers share the same physical hardware, separated logically. This is the standard Azure model most people think of. Second, the private cloud. This uses cloud technologies but an environment dedicated to a single organization. It might be hosted in your own data center or with a partner, but the key idea is exclusivity and control. Third, the hybrid cloud, which combines on-premises resources with public cloud. This allows workloads and data to move between your data center and Azure. Many real-world customers are hybrid because they have existing systems they can't move immediately. You'll also hear multi-cloud, where organizations use multiple public cloud providers. AZ-900 doesn't go very deep here, but it's useful context. Each model has trade-offs in control, compliance, cost, and complexity. Public cloud gives maximum agility. Private cloud gives maximum control, and hybrid sits in the middle. In the next two slides, we'll zoom in on public cloud and then private and hybrid cloud with practical use cases, so you can recognize them in exam scenarios. Let's zoom in on public cloud and see where it shines. Public cloud is ideal for startups and new projects that need to move fast without buying expensive hardware. You can spin up resources in minutes and shut them down if the idea doesn't work. It's excellent for global applications. By deploying your app into multiple Azure regions, you can serve users closer to where they are, reducing latency and improving experience. Public cloud is also perfect for variable or unpredictable workloads. Think about an e-commerce site during Black Friday or a ticketing site during a big launch. You don't want to own hardware for the peak all year. Public cloud lets you scale up for the peak and scale down afterwards. It's useful for innovation and experimentation. Teams can create test environments quickly, try new services like AI or analytics, and then tear them down. You can also use public cloud for backup and disaster recovery. replicating data or critical systems from on-premises to Azure, without building a second physical data center. An easy analogy: public cloud is like renting co-working space. Instead of building your own office, you get flexibility and shared facilities, and you only pay for what you actually use. Next, we'll balance the picture by looking at private and hybrid cloud scenarios, where organizations need more control or have special regulatory requirements. Now, let's look at situations where public cloud alone isn't enough and private or hybrid approaches make more sense. Private cloud is used when organizations need strong control over where data lives and how it's handled. Industries like finance, government, and healthcare often have strict regulatory or security requirements that make dedicated environments attractive. Hybrid cloud connects your on-premises environment with Azure. This is very common in large enterprises. They might keep a core database or mainframe on-prem because of latency, compliance, or technical reasons, and move front-end applications or new services to Azure. Hybrid is also great for gradual migration. Instead of moving everything at once, you move workloads in phases, testing as you go. If something doesn't fit well in the cloud yet, you keep it on-prem and revisit it later. A powerful pattern is cloud bursting. You run workloads on-prem most of the time, but when demand spikes beyond your local capacity, extra loads run in the cloud. Think of it like this: your house is your on-prem environment, giving comfort and control. When guests overflow the house, you rent extra rooms in a hotel. That's the public cloud. Combining them is hybrid. Next, we'll switch from where things run to how you pay for them by looking at the consumption-based model that underpins cloud economics. On this slide, we'll talk about how cloud is built and what consumption-based really means. In a traditional data center, you make capital expenditure, CapEx. You buy servers, storage, and networking up front, whether you use them fully or not. In the cloud, most costs become operational expenditure, OpEx. You pay based on what you actually consume. A consumption-based model means you are charged for metrics like the number of running hours for a VM, the amount of data stored, or the number of operations performed. If you shut down resources, your costs drop. If you use more, your bill increases. This gives you cost flexibility and transparency. You can see how much each resources cost and adjust configurations to optimize spend. It also supports chargeback, where different departments pay for the resources they consume. However, there's also a risk. Without governance, it's easy for people to create resources and forget them, leading to unexpected bills. That's why tagging, budgets, and policies are important. A good analogy is your utility bill. You don't pay a flat fee for infinite electricity. You pay for the units you consume. Cloud just applies this to compute, storage, and network. In the next slide, you'll build on this idea and compare different cloud pricing models, such as pay-as-you-go, reserved instances, and spot pricing, so you know which one fits which scenario. Now that you understand consumption-based billing, let's compare the main pricing options Azure offers. The most flexible is pay-as-you-go. You're billed by usage with no long-term commitment. This is ideal for dev test environments, experiments, and unpredictable workloads. Next, we have reservations or reserved instances for certain services. Here, you commit to using a resource, for example, a VM size, for 1 or 3 years. In return, you get significant discounts. This is great for steady, always-on workloads where usage is predictable. Then there is spot pricing, where you use unused Azure capacity at a much lower price. The trade-off is that Azure can take the capacity back when it's needed, so workloads must tolerate interruptions. This suits batch jobs, testing, or non-critical processing. Many services also offer a free tier or limited free usage per month. That's useful for learning, demos, or very small workloads. Larger organizations may have enterprise agreements, where they negotiate pricing and credits with Microsoft. From an exam perspective, focus on matching the workload pattern to the pricing model. Variable usage, pay as you go. Stable baseline, reservations. Interruption tolerant, spot. Next, we'll see how Azure takes the consumption idea even further with serverless computing, where you don't even think in terms of servers at all. In this slide, we'll demystify serverless computing, a term that shows up a lot in modern cloud discussions. Serverless does not mean there are no servers. It means you don't manage the servers. Azure automatically handles provisioning, scaling, and patching. You focus purely on your business logic. The main Azure example is Azure Functions. Here, you write small pieces of code called functions that run in response to events. An HTTP request, a message on a queue, a timer trigger, a file upload, and so on. With the consumption plan, you pay based on the number of function executions, memory used, and execution time. If your function doesn't run, you don't pay compute costs. This makes serverless very cost-efficient for spiky or low-volume workloads. Serverless functions are typically stateless. If you need to persist data or state, you use other services like storage accounts, databases, or durable function patterns. Typical use cases include APIs, background processing, IoT data handling, scheduled jobs, and glue code between systems. A simple analogy is a taxi or ride-hailing service. You don't own the car or worry about maintenance. You just request a ride when you need it and pay for the trip. In the next slide, we'll connect this back to high availability and scalability and see how cloud, serverless or not, helps your application stay online and responsive under changing load. On this slide, we'll connect cloud computing to two critical ideas: high availability and scalability. High availability means designing systems so that they stay up and running with minimal downtime, even when something goes wrong. In the real world, hardware fails, network links drop, and software crashes. Azure helps you handle this by providing redundancy. Instead of running a single virtual machine, you might run multiple instances behind a load balancer. If one instance goes down, the others can continue serving users. Azure also offers availability zones, which are physically separate data centers within the same region. By placing instances across zones, you protect against the failure of an entire building or site. The exam doesn't expect deep configuration details, but it does expect you to recognize that availability zones and multiple instances are tools for high availability. Now, scalability is about handling changing load. When demand increases, you add capacity. When it decreases, you remove it. There are two main approaches: vertical scaling, giving a resource more CPU, memory, or storage; horizontal scaling, adding more instances of the resource. Azure supports auto-scaling, where you define rules based on metrics like CPU usage, HTTP queue length, or message count. When those thresholds are hit, or others, Azure automatically scales out or in. This allows your application to remain responsive when traffic spikes and cost-efficient when it fails. Together, high availability and scalability ensure that your application is both reliable and responsive, even under unpredictable load. In the next slide, we'll build on this and look at reliability and predictability. Not just staying online, but staying consistent over time in both performance and cost. Here, we'll shift from surviving failures in the moment to thinking about long-term reliability and predictability. Reliability means that your system consistently does what it's supposed to do over time. A reliable system doesn't just handle a single failure gracefully, it has processes and patterns that ensure users can trust it day after day. One part of this is fault tolerance. In Azure, that often means designing your application so that if one component fails, another can take over. For example, running multiple instances of your web app or replicating your database to another region as a standby. Another important aspect is backup and disaster recovery. Azure gives you services like Azure Backup and features like geo-redundant storage to keep copies of your data. If data is accidentally deleted, corrupted, or a region experiences a major outage, you have a plan to recover. Now, let's talk about predictability. In the cloud, you want predictable performance and predictable costs. Predictable performance means your application responds consistently under expected load. You achieve this by choosing appropriate resource sizes, using scaling and monitoring regularly. Predictable costs come from understanding your pricing model, setting budgets and alerts, and using tools like Azure Cost Management. Over time, you'll learn the typical monthly cost of each workload and avoid financial surprises. A helpful analogy is public transport. In a well-run city, buses arrive when they're supposed to, routes are clear, and delays are rare. You might not control every detail, but overall, the system behaves in a reliable and predictable way. Next, we'll look at another huge reason organizations adopt Azure: the security and governance benefits that come built into the platform. On this slide, let's see how Azure helps with security and governance, two of the most important topics for any organization. First, centralized security. Instead of securing dozens of separate data centers and ad hoc systems, you can apply consistent controls across your Azure environment. Identity, network, data, and application security can be managed from central services. At the heart of Azure security is Microsoft Entra ID, which provides identity and access management for users, groups, and applications. You can enforce multi-factor authentication, single sign-on, and conditional access policies from one place. For data protection, Azure supports encryption at rest and in transit. Storage accounts, databases, and disks can be encrypted, and you can enforce HTTPS and TLS for data in motion. On the network side, you have tools like network security groups, Azure Firewall, and DDoS protection. These help control and shield traffic into and out of your resources. With private endpoints, you can keep traffic on Microsoft's backbone instead of exposing public endpoints. Now, let's talk governance. Governance is about setting rules and guardrails so teams can move fast without breaking organizational policies. With Azure Policy, you can enforce things like only these regions are allowed or all storage must be encrypted. You can also use tags and management groups to organize and control resources. Azure also aligns with many compliance standards, like ISO and SOC, which helps organizations meet regulatory requirements. In short, Azure doesn't just give you raw compute and storage. It gives you security and governance frameworks to run responsibly at scale. Next, we'll see how Azure makes all of this manageable day to day by looking at the manageability benefits of the cloud. Now that we've discussed security and governance, let's look at how Azure makes environments easier to manage, especially at scale. First, there's the Azure portal. This is a unified, web-based interface where you can create, view, and manage nearly all Azure resources. You can see dashboards, metrics, and configuration settings in one place without installing anything locally. But the portal is just one option. Azure also provides automation tools like the Azure CLI and Azure PowerShell, which let you manage resources from the command line. This is powerful for repeatable tasks and for integrating into scripts and pipelines. Then we have Infrastructure as Code, IAC. Instead of clicking through wizards, you describe your environment in templates, such as ARM templates or bicep files, and deploy them consistently across development, test, and production. This reduces human error and makes changes traceable and version controlled. On the observability side, Azure Monitor, Log Analytics, and Application Insights collect metrics and logs from across your environment. You can set up dashboards and alerts so you know when something goes wrong before users do. Role-based access control, RBAC, lets you delegate responsibilities safely. For example, you can give a team contributor access to just one resource group instead of handing over subscription-wide permissions. A helpful analogy: think of Azure like a smart home. Instead of manually switching every light and thermostat, you have a central app and automation rules that keep everything in sync. Next, To wrap up this module, we'll connect everything back to the cloud services type, IaaS, PaaS, and SaaS, and see when to choose each model. To close this first module, let's pull the concepts together by revisiting the three main cloud services type: IaaS, PaaS, and SaaS, along with typical use cases. Infrastructure as a service, IaaS, gives you the most control. You get virtual machines, storage, and networking, and you manage the operating system, runtime, and applications. This is ideal for lift and shift migrations, where you move an existing application from on-prem to the cloud with minimal changes. For example, taking a legacy app currently running on a physical server and hosting it on Azure VM. Platform as a service, PaaS, abstracts away the underlying infrastructure. With PaaS, like Azure App Service or Azure SQL Database, you focus on your application or data, and Azure manages the OS, patches, and most scaling. This is excellent for modern web apps and APIs where you want productivity and built-in features like deployment slots or auto-scale. Software as a service, SaaS, delivers fully managed applications over the internet. Examples include Microsoft 365, Dynamics 365, or other business apps. You don't manage servers or even application deployment. You just configure and use the software. SaaS is great when you want functionality quickly without building it yourself. The key exam question is usually, how much control versus convenience does the customer need? More control and responsibility? Likely IaaS. Balance of control and productivity? Usually PaaS. Minimal responsibility, just use the app? SaaS. With that, you've covered the core cloud concepts AZ-900 expects. In the next module, we'll move from general cloud ideas into how Azure itself is structured globally and what its core services look like in practice. In this slide, we'll start exploring how Azure is built at a global level, its physical and logical infrastructure. Azure is made up of a worldwide network of Microsoft-managed data centers. These data centers are grouped into regions, which are geographic areas like UK South, West Europe, or East US. When you deploy resources, you normally choose a region, and that's where your resources physically live. Azure regions are connected by Microsoft's high-speed private backbone network, which help deliver low latency and high reliability between locations. This private network is one of the many reasons enterprises trust Azure for mission-critical workloads. Many regions are organized into region pairs. For example, UK South is paired with UK West. Region pairs are used for things like coordinating updates and supporting disaster recovery scenarios. If one region faces a major outage, services can fail over to its pair. Azure also includes special sovereign or government regions, which are isolated to meet strict regulatory and compliance requirements. You don't need to memorize all of them. Just understand that they exist to satisfy certain countries' laws and public sector needs. The goal of this global infrastructure is to provide low-latency access to users around the world, while delivering resilience and data residency options. In the next slides, we'll zoom in further and look at regions, region pairs, and availability zones in more detail, so you can recognize how they support high availability and disaster recovery designs. Now let's dig deeper into regions, region pairs, and sovereign regions, and why they matter for design and for the exam. A region is a set of data centers deployed within a specific geographic area. When you create a VM, storage account, or a database, you almost always select a region. Choosing a region close to your users can reduce latency and improve performance. Azure pairs most regions with another nearby region, forming a region pair. For example, an exam question might mention that UK South is paired with UK West. Region pairs are designed so that platform updates are rolled out to paired regions in a staggered way, reducing the chance both go down simultaneously. In certain disaster scenarios, recovery operations are prioritized across the pair. This is useful when planning disaster recovery. You might run your primary workload in one region and keep a standby in its paired region. Sovereign regions are specialized Azure regions designed to meet specific legal and compliance requirements, often for governments and public sector organizations. Access is more restricted and data residency is tightly controlled. For the AZ-900, you don't need to know every region name, but you should understand. Regions is where resources live. Region pairs is resilience and update coordination. Sovereign regions are specialized, compliance-focused environments. Next, we'll narrow down even further to understand availability zones and individual data centers and how they help you build high available architectures inside a region. On this slide, we'll talk about availability zones and data centers and how they support resilience within a single region. A data center is the physical facility that houses servers, storage, and networking equipment. A single Azure region can contain multiple data centers. Availability zones are unique physical locations within a region, each made up of one or more data centers with independent power, cooling, and networking. The important idea is fault isolation. A problem in one zone, like a power issue, should not take down the others. When you deploy zone-redundant services, Azure spreads instances across multiple zones. For example, you can run your application in Zone 1, Zone 2, and Zone 3. If one zone fails, traffic can be routed to the remaining zones, increasing availability. Some resources are zonal, meaning you can pin them to a specific zone, which can be useful for low-latency scenarios or aligning to on-premise connectivity. You'll also hear about fault domains and update domains. Fault domains group resources that share a common power source or network switch, while update domains control how planned maintenance is rolled out. Together, they help reduce the risk of simultaneous failures. A helpful analogy. Think of a university campus. Each building is like a data center, and a group of buildings on different parts of the campus are like separate zones. A problem in one building shouldn't shut down the entire university. In the next slide, we'll move up a level from the physical layout and talk about resources and resource groups, which are the logical building blocks you'll interact with in Azure every day. On this slide, we'll look at some of the core logical building blocks in Azure: resources, resource groups, and overall hierarchy. A resource is any manageable item in Azure. That includes virtual machines, storage accounts, web apps, SQL databases, virtual networks, and many more. Whenever you create something in Azure, you're creating a resource. Resources are organized into resource groups. A resource group is a logical container that holds related resources that share the same lifecycle. For an example, all the components of a web application, its web app, database, storage, and virtual network, might live in a single resource group so you can manage them together. The Azure scope hierarchy goes like this: management groups, subscriptions, resource groups, resources. Policies and access permissions, like RBAC, can be applied at any of these levels, and they inherit downwards. If you assign a role at the subscription level, by default it applies to all resource groups and resources inside that subscription. A common exam point: resource groups are for lifecycle and management, not for isolation, like networks or security groups. You can move some resources between groups, deploy templates into a group, or delete an entire environment by deleting its group. Design-wise, you typically group resources by application, environment, and ownership. For example, rg-app1-prod for production resources of app1. A helpful analogy is a project folder on your computer. Inside that folder, you keep all related files together so you can manage, copy, or delete them as a single unit. Next, we'll climb one step higher in the hierarchy and look at subscriptions and management groups, which are crucial for billing, access, and governance across larger environments. Now let's talk about subscriptions and management groups, which form the backbone of organizations and billing in Azure. An Azure subscription is essentially a billing and security boundary. All resources in Azure belong to exactly one subscription. Your monthly invoice is generated per subscription, and access control is often applied at this level. Think of a subscription as a container for resource groups and resources, tied to a billing account. Organizations often use multiple subscriptions for separation. For example, you might have different subscriptions for production, test, and development, or separate subscriptions for different departments or business units. This makes it easier to manage costs, access, and policies independently. Above subscriptions, you have management groups. A management group can contain multiple subscriptions and other management groups forming a tree. This is where you apply governance at scale. For instance, you can assign an Azure policy or a role at a management group level, and it will automatically apply to all child subscriptions and their resources. This hierarchy is a key AZ-900 concept. Management groups is organization-wide governance. Subscriptions are billing boundary and access boundaries. Resource groups is logical grouping by application or life cycle. And resources are the actual services you use. Management groups are like head office. Subscriptions are individual branches. Resource groups are departments within a branch, and resources are people and equipment. In the next slide, we'll shift from structure to execution and compare the different Azure compute options you can run inside these subscriptions and resource groups. On this slide, we'll compare the main Azure compute options you'll see in AZ-900 scenarios and learn when to choose each one. First, virtual machines, VMs. These give you the most control over the OS and runtime. You choose the image, manage patches, and configure everything. They're ideal for lift and shift migrations and workloads that need custom setups. Next, Azure Container Instances, ACI. These let you run containers directly without managing the underlying VM. You package your app in a container image and Azure runs it for you. Great for simple container workloads, jobs, or small services. Azure Kubernetes Service, AKS, is a managed Kubernetes offering. It's used when you have many containers and microservices, need advanced orchestration features, rolling updates, and service discovery. For the AZ-900, just remember, AKS equals Managed Kubernetes for Containerized Apps at Scale. Azure App Service is a PaaS option for hosting web apps and APIs. You don't manage servers or the OS, just deploy your application. It's a good default for web front ends. Azure Functions provides serverless, event-driven compute. You write small functions that run when triggered by events. Ideal for background processing, APIs, or automation. Finally, Azure Virtual Desktop delivers hosted Windows desktops and remote apps from Azure, useful for secure remote working. For the exam, focus on matching scenarios. Need full control? Custom OS? VMs. Simple container execution? ACI. Large microservice environment? AKS. Web apps, APIs? App service. Event-driven, pay per execution. Functions. Next, we'll look more closely at Azure virtual machines themselves and the various options and features they provide. In this slide, we'll dive deeper into Azure virtual machines, VMs, and understand the options available when you choose IaaS Compute. When you create a VM, you choose a VM size that defines CPU, memory, and storage performance. Azure offers size families optimized for different needs. General purpose, compute optimized, memory optimized, storage optimized, and GPU for graphics or compute-intensive tasks. You also choose a VM image, which is essentially the template for the operating system and pre-installed software. Azure Marketplace provides many images, Windows servers, various Linux distros, databases, and application stacks. You can also create custom images to standardize your deployments. For resiliency, Azure provides availability sets and scale sets. An availability set spreads VMs across fault domains and update domains within a data center, reducing the chance they all go down together due to hardware failure or maintenance. A virtual machine scale set lets you manage a group of identical VMs, often with autoscaling based on demand. Storage is another key choice. You attach OS disks and data disks using different SKUs like standard HDD, standard SSD, or premium SSD, each with different performance and cost. Azure also offers spot VMs, which use spare capacity at a big discount but can be reclaimed by Azure when needed. These are suitable for non-critical, interruptible workloads. In short, VMs are your flexible, low-level building blocks when you need maximum control and compatibility with traditional workloads. Next, we'll see what's required around a VM, networking, storage, identity, and backups, by exploring VM dependencies and requirements. On this slide, we'll look at the dependencies and requirements that come along with running virtual machines in Azure. First, every VM lives inside a virtual network, or VNet. This VNet provides a private IP addressing and connectivity. Within the VNet, you place the VM in a subnet, which is a segment of the address space. To control traffic, you typically associate a network security group, NSG, with the subnet or the VM's network interface. NSGs act like firewalls, allowing or denying inbound and outbound traffic based on rules. For example, you might allow HTTP and HTTPS inbound, but block everything else. On the storage side, each VM has an OS disk and may have one or more data disks. These are stored in Azure Managed Storage and can use different performance tiers. Some VM types also have temporary disks for short-lived data. For identity and secure access to other Azure services, you can use managed identities for Azure resources. This avoids hard-coding credentials in your code. Instead, the VM's identity is used to request tokens from Entra ID. Monitoring and management are also important dependencies. You can install agents to send metrics and logs to Azure Monitor and Log Analytics, enabling insights and alerts. For protection, you can configure Azure Backup to take regular snapshots so you can restore the VM or individual files if something goes wrong. Here's the key takeaway. A VM is not just a standalone server. It relies on networking, storage, identity, monitoring, and backup services around it. Next, we'll move from raw infrastructure to platform services by exploring the main application hosting options in Azure. In this slide, we'll examine how to host applications in Azure beyond just running them on virtual machines. One of the most popular options is Azure App Service, a platform as a service that hosts web apps, REST APIs, and background jobs. You don't manage the underlying OS or web server, you just deploy your code. App Service supports multiple languages and frameworks like .NET, Java, Node.js, Python, and PHP. App Service runs on an App Service plan, which defines the pricing tier, region, and compute resources. Higher tiers unlock features like auto-scaling, deployment slots, and custom domains. For static front ends plus serverless backends, there's Azure Static Web Apps, which combines static site hosting with integrated Azure functions for APIs. This is great for Jamstack-style applications. If your app is already containerized, you can deploy containers directly to Web App for Containers, part of App Service, or run them on Azure Container Apps or Azure Kubernetes Service, AKS, for more complex microservices architectures. Azure also offers Azure Spring Apps for Spring Boot microservices and other specialized PaaS options. Choosing between these depends on your architecture and operational preferences. Want maximum control? VMs or AKS. Want managed platform for web APIs? App Service. Want static front end plus serverless backend? Static web apps and functions. For the AZ-900, focus on recognizing each option and matching it to simple scenarios. Next, we'll return to networking fundamentals and look at virtual networks, subnets, and peering which are the foundation of connectivity in Azure. On this slide, we'll cover virtual networks, VNets, subnets, and VNet peering, which form the basis of networking in Azure. A virtual network is your private network space in Azure. It's similar to a network on your on-premises data center, but defined in software. When you create a VNet, you specify an address space using CIDR notation. For example, 10.0.0.0/16. Within a VNet, you create subnets, which carve that address space into smaller segments. Subnets help you logically separate different tiers or functions such as front-end, application, and database layers. You can apply network security groups, NSGs, at the subnet level to control which traffic is allowed in or out. VNets are isolated from each other by default. To let resources in different VNets communicate, you can configure VNet peering. Peering connects VNets over the Azure backbone network with low latency and high bandwidth, without sending traffic over the public internet. There are two main flavors: VNet peering within the same region, and global VNet peering, which connects VNets across different regions. Once peered, resources can talk to each other using private IP addresses, subject to NSG and routing rules. Think of a VNet as your company's private office network on a floor in a building. Subnets are different departments on that floor. VNet peering is the private corridor connecting your floor to another office in a different building, still within your corporate campus. Next, we'll build on these concepts by examining Azure DNS and name resolution, which is how names like app.contoso.com turn into IP addresses inside Azure environments. On this slide, we'll look at Azure DNS and how name resolution works inside Azure environments. In any network, users and applications prefer to use names like app.contoso.com rather than raw IP addresses. Something needs to translate those names into IPs. That's the job of DNS, the domain name system. Azure DNS is a hosting service for DNS domains in Azure. You can host your public DNS zones there, which means Azure globally distributed DNS infrastructure answers queries for your domain. This gives you high availability and low latency name resolution for internet-facing names. You can create and manage DNS records types such as A, IPv4 addresses, AAAA, IPv6, CNAME, alias, TXT for text, MX for mail, and others, directly from the Azure portal, CLI, or templates. For internal networks, Azure also offers private DNS zones. These provide name resolution inside one or more virtual networks without exposing those names to the public internet. For example, you might have a private name like database.internal.contoso.local, resolving to a private IP in your VNet. You link virtual networks to a private DNS zones, so VMs and services in those VNets automatically use that private DNS to resolve names. Name resolution in Azure typically follows this pattern: public names, public Azure DNS or another provider; internal names, private DNS zones or custom DNS servers. A useful analogy is like a phone book. DNS maps human-friendly names to phone numbers, your IP addresses, making it easier for people and systems to connect to the right place. Next, we'll move from naming to secure connectivity between on-premises and Azure, starting with VPN gateway and hybrid connectivity options. On this slide, we'll explore Azure VPN gateway and the main connectivity options it provides for hybrid scenarios. An Azure VPN gateway is a specific type of virtual network gateway that establishes encrypted tunnels between Azure virtual networks and other locations, such as your on-premises data center or individual client devices. There are two primary VPN scenarios. 1. Site-to-site VPN. This connects an entire on-premises network to an Azure VNet, using IP security (IKE) tunnels between your on-prem VPN device, like a hardware firewall, and the Azure VPN gateway. Once established, Machines on both sides can communicate as if they're on the same extended network. 2. Point-to-site VPN. This allows individual client devices, like a laptop, to connect securely to Azure. Users install a VPN client and authenticate, establishing an encrypted tunnel into the VNet. This is useful for remote workers or admins needing secure access. Azure offers different gateway SKUs with varying throughput, features, and SLAs. For higher availability, you can deploy VPN gateways in active standby or active-active configurations. These VPN connections protect data in transit by using industry-standard protocols, IPsec/IKE, which is important for compliance and security-sensitive workloads. In many architectures, VPN is the first step into hybrid, relatively easy to set up, secure, and flexible. Later, organizations may adopt more advanced connectivity like ExpressRoute for higher reliability and performance. Next, we'll build on this by looking at ExpressRoute and hybrid connectivity, which offer private, dedicated connections into the Microsoft backbone network. Here, we'll look at Azure ExpressRoute, which is another major option for connecting on-premises environments to Azure. While VPN gateways connect over the public internet using encrypted tunnels, ExpressRoute provides a private, dedicated connection into Microsoft's network through a connectivity provider or co-collation facility. This means your traffic doesn't traverse the public internet at all. The benefits are higher reliability, more consistent latency, and potentially higher bandwidth than typical internet VPNs. Because the path is private and controlled, ExpressRoute is often used by banks, governments, and large enterprises for critical workloads. ExpressRoute supports different peering options, including private peering for traffic to Azure VNets, and Microsoft peering for accessing Microsoft SaaS services like Microsoft 365 in some scenarios. For resiliency, many organizations combine ExpressRoute with VPN. If the private circuit fails, a site-to-site VPN can serve as a backup path, improving availability. From an AZ-900 perspective, you don't need deep configuration skills, but you should know when to choose ExpressRoute. When you need private, non-internet connectivity. When predictable performance and reliability are critical. When regulatory requirements discourage using the public internet. Think of VPN as a secure tunnel over public roads, while ExpressRoute is like having a private highway directly into Microsoft's network. Next, we'll zoom into how individual services are exposed by looking at public endpoints, private endpoints, and service endpoints, and when each is appropriate. On this slide, we'll clarify three related but distinct concepts: public endpoints, private endpoints, and service endpoints for Azure services. A public endpoint is an IP address reachable over the public internet. Many Azure PaaS services, like storage accounts or web apps, originally exposed public endpoints so clients anywhere could connect. While convenient, public endpoints can increase your attack surface if not secured properly. A private endpoint provides a private IP address inside your VNet for a PaaS service. With private endpoints, traffic between your resources and the service flows over the Azure backbone, not the public internet. This dramatically improves security and is often recommended for production scenarios where you want tight access control. Service endpoints are slightly different. They extend your VNet's identity to specific PaaS services. Traffic still goes to the service public endpoint, but Azure recognizes that it comes from a specific VNet subnet and allows you to restrict access to that VNet. It's more about access control than private addressing. In many modern designs, private endpoints are preferred for sensitive data services like storage or SQL, while service endpoints are still used in some simpler scenarios. From an exam standpoint, remember, public endpoint, accessible from the internet with appropriate firewalls; private endpoint, service appears inside your VNet with a private IP; service endpoint, secure access from a VNet to a public PaaS endpoint. Next, we'll change gears from networking back to data and look at Azure Storage Account and its main services. In this slide, we'll explore the Azure storage account and the different storage services it provides. A storage account is a top-level container that gives you a unique namespace and a set of capabilities for storing different types of data. When you create a storage account, you choose options like performance tier, redundancy, and account kind. For example, general purpose V2. Inside a storage account, you have several core services. 1. Blob storage, for unstructured data such as images, videos, documents, and backups. Blobs are ideal for large files and binary data. 2. File shares, Azure files. SMB or NFS-based file shares that can be mounted by Windows, Linux, or Mac OS. Great for lift and shift of applications that expect a traditional file server. Queue storage. Simple, reliable message queues for communication between components. For example, a web app might put messages onto a queue and a background worker processes them. 4. Table storage, a NoSQL key value store for semi-structured data. It's useful when you need fast access to simple entities without the overhead of a relational database. There are also disk resources, managed disks, that are technically separate but conceptually belong to the broader storage story. The exam will often ask, given a scenario, which storage type is most appropriate. Think along these lines: big files, blob; shared drive, files; asynchronous messages, queues; simple structured data, tables. Next, we'll look at storage tiers and redundancy options, how you optimize cost and durability based on how often you access your data and how resilient it needs to be. Now let's talk about two key aspects of Azure storage: access tiers and redundancy options. For blob storage, Azure offers access tiers that help you optimize cost. Hot tier, designed for data that is accessed frequently. It has higher storage costs but lower access and retrieval costs. Cool tier, for infrequently accessed data that you still need to keep online. Lower storage costs than hot, but higher access charges and minimum retention periods. Archive tier, for rarely accessed data, like long-term backups or compliance archives. It's the cheapest to store, but data is offline and must be rehydrated before you can access it, which takes time and incurs higher retrieval costs. Choosing the right tier depends on how often you read the data and how quickly you need it. Now, redundancy. Azure offers several options to protect against hardware and regional failures. LRS, locally redundant storage, keeps 3 copies of your data within a single data center. ZRS, zone redundant storage, spreads data across multiple availability zones within a region. GRS, geo-redundant storage, replicates data asynchronously to a secondary region hundreds of kilometers away. RA-GRS, read access GRS. It's like GRS, but allows read access to the secondary region. In AZ-900 scenarios, you'll often choose between these based on how critical the data is and your disaster recovery requirements. Next, we'll see how to actually move data into and around Azure storage using tools like AZ Copy, Storage Explorer, and Azure File Sync. On this slide, we'll look at the main data movement and management tools for Azure storage: AZ Copy, Storage Explorer, and Azure File Sync. AZ Copy is a command line tool designed for high-performance transfers to and from Azure storage. You can use it to upload, download, and copy blobs, files, and other storage objects. Because it's scriptable, it's great for automation. For example, migrating a large dataset overnight or syncing backups. Azure Storage Explorer is a graphical desktop application. It provides a friendly GUI to browse containers, blobs, file shares, queues, and tables. You can upload and download files, manage metadata, and inspect data without writing any code. It's especially handy for admins and developers who want quick, visual access. Azure File Sync is different. It's designed to synchronize on-premises Windows file servers with Azure files. The idea is that your most used files stay cached on-prem, but the full dataset lives in Azure. This helps modernize file server infrastructures while keeping local performance for branch offices. When planning data movement, you also consider network bandwidth, scheduling, and throttling, so you don't overwhelm your connection or impact business hours. From an exam point of view, need scripted bulk transfers? AZ Copy. Need GUI-based management and inspection? Storage Explorer. Need to extend or replace on-prem file servers? Azure File Sync. Next, we'll move from data migration to workload migration as a whole by looking at Azure Migrate and Azure Data Box as key options for moving entire environments into Azure. Migration is one of the biggest reasons organizations touch Azure, so it's worth having a clear mental model for the main tools: Azure Migrate and Azure Data Box. Azure Migrate acts as a central hub for discovery, assessment, and migration of on-premises workloads into Azure. You install lightweight agents or appliances in your environment so Azure Migrate can discover servers, databases, and applications, then gather performance data over time. Based on this data, Azure Migrate can produce assessment reports, which VMs are ready to move, what size they should be in Azure, estimated costs, and any compatibility concerns. From there, you can trigger actual migrations, often integrating with other tools like Database Migration Service. This supports several scenarios: server migration of VMware or Hyper-V virtual machines, database migration to Azure SQL or managed instance, application-level assessments to see dependencies between components. Azure Data Box solves a different problem: how to move huge volumes of data when your network is the bottleneck. Instead of pushing tens of terabytes over the internet, you order a physical data box device from Microsoft. You copy your data onto the device locally, ship it back, and Microsoft uploads it directly into Azure storage. DataBox is ideal when you have limited bandwidth, time constraints, or remote locations where network transfers are impractical. A good way to remember this split: Azure Migrate is for planning and executing workload migrations. Azure Data Box is for bulk data transfer using physical devices. Next, we'll move from migration into identity and directory services by looking at Microsoft Entra ID and how it underpins authentication in Azure. Identity is at the center of almost everything you do in Azure, and Microsoft Entra ID, formerly Azure AD, is the cloud identity platform that makes it work. Every organization using Azure has an Entra tenant, a dedicated instance of that directory that holds users, groups, application registrations, and service principals. This tenant is where you define who people are and what they can access. Entra ID provides authentication and single sign-on (SSO) across Azure, Microsoft 365, and many third-party applications. Users sign in once and then access multiple apps without repeatedly entering their password, which improves both security and user experience. For scenarios where legacy applications expect traditional domain services, Microsoft offers Entra Domain Services. This provides domain join, LDAP, and Kerberos capabilities, without you having to run your own domain controllers in the cloud. Entra ID also supports external identities. With B2B collaboration, you can invite guest users from other organizations into your tenant. With B2C, you can authenticate customers using local accounts or social logins. Hybrid identity is very common. Organizations sync their on-premises Active Directory to Entra ID using tools like Azure AD Connect, so users have a single identity across cloud and on-prem systems. Security-wise, Entra enables passwordless authentication options like FIDO2 security keys and the Microsoft Authenticator app, reducing reliance on passwords alone. A simple analogy is that Entra ID is both the company phone book and the passport office for the cloud. It knows who everyone is and issues the credentials they use. Next, we'll build on this foundation and talk about authentication, RBAC, conditional access, and zero trust, which define how identity is actually used to control access. Identity by itself isn't enough. You also need solid access control and security policies based on that identity. Authentication is the process of proving who you are. For example, by providing a password, using a security key, or responding to a push notification. Once you're authenticated, Azure issues tokens that represent your identity to different services. Authorization is the process of deciding what you're allowed to do after authentication. In Azure, the main mechanism is role-based access control, RBAC. You assign built-in or custom roles like reader, contributor, or owner at different scopes. Management group, subscription, resource group, or resource. Permissions flow down the hierarchy. Conditional access adds rules on top of authentication. You can say things like require MFA if the user is outside the corporate network. Block access from certain countries or insecure devices. Require compliant devices for sensitive applications. The broader security philosophy is zero trust. Rather than trusting anything just because it's inside the corporate network, zero trust says, never trust, always verify. Every request must be authenticated, authorized, and evaluated based on context. To strengthen this further, Azure encourages defense in depth. Multiple security layers add identity, endpoints, network, applications, and data. Finally, Microsoft Defender for Cloud sits on top as a unified security posture management tool. It analyzes configurations, recommends improvements, and can detect suspicious activity across your Azure and even multi-cloud resources. Next, we'll switch gears from identity and security to money, starting with the key cost factors in Azure that drive your bill. Understanding what drives cost in Azure is essential for both the exam and real life. Think of your Azure bill as the sum of several major categories. The biggest driver is usually compute. Virtual machines, app service plans, AKS node pools, and other compute services charged based on size, type, and uptime. A large VM running 24/7 will dominate the bill compared to a small one only used in office hours. Next comes storage. Cost depends on how much data you store. The tier, hot, cool, archive, and the redundancy option, LRS, ZRS, GRS, etc. Premium SSD disks, for example, cost more than standard HDDs. Networking is another factor. Inbound data to Azure is typically free, but outbound data transfer to the internet, VPN connections, or ExpressRoute circuits can add up, especially for bandwidth-heavy workloads. Licensing can also be significant. Running Windows Server or SQL Server on Azure may incur additional licensing costs unless you use options like Azure Hybrid Benefit to reuse existing licenses. Support plans such as Developer, Standard, or Professional Direct add a fixed monthly fee for enhanced support and faster response times. On top of all of this, you might pay for PaaS and SaaS services, like databases, analytics, or AI APIs, each with their own pricing meters. The key idea for AZ-900, cost is driven by what you run, how big it is, how long it runs, where it's located, and how much data moves in and out. Next, we'll see how to estimate those costs ahead of time using the Azure pricing calculator, so there are fewer surprises after deployment. The Azure pricing calculator is your primary tool for estimating monthly costs before you deploy anything. You start by selecting the services you plan to use, virtual machines, storage accounts, databases, app service, and so on. For each service, you configure key options. Region, since prices can vary by region. SKU or size, example being VM type, DTU level. Quantity, how many instances, and usage pattern, hours per month, storage amount, transactions, etc. The calculator then shows an estimated monthly cost for each service and a total for the solution. You can adjust variables like the number of users, request volume, or storage size to see how the estimate changes. Results can be exported as an Excel spreadsheet or a shareable URL so you can discuss them with finance teams, managers, or clients. This is especially helpful when you need to compare multiple architectural options side by side. For example, using VMs versus app service or different redundancy levels. The tool is most accurate when you provide realistic usage assumptions, so it's worth gathering basic performance and usage data from your existing systems if you can. For the AZ-900, remember that the pricing calculator is about forecasting and planning. It doesn't control billing itself, it just helps you model costs before committing to a design. Next, we'll look at what happens after deployment, how you monitor, analyze, and control actual spending using Azure Cost Management and Billing. While the pricing calculator helps you estimate future costs, Azure Cost Management and Billing helps you understand and control current and historical spending. Cost Management provides dashboards and reports showing how much you're spending by subscription, resource group, service, region, or tag. You can drill down to see which workloads or teams are driving costs and identify trends over time. You can define budgets for a subscription or resource group. A budget sets a threshold, for example, $500 per month, and when your actual or forecasted spend crosses certain percentages, like 50%, 75%, or 100%, Cost Management can send alerts by email or to action groups. There's also a cost analysis feature that lets you slice and filter costs along different dimensions, such as service type, location, or tag values. This is essential for chargeback or showback models, where departments are accountable for their cloud usage. Recommendations may highlight idle or underutilized resources. For example, VMs with very low CPU usage or unattached disks, so you can right-size or clean them up. On the billing side, you can manage billing accounts, invoices, payment methods, and view the breakdown of charges. Enterprise customers might see additional hierarchies and enrollment features. The main exam takeaway: Cost Management and Billing are there to monitor, analyze, and optimize actual spend once resources are running. Next, we'll see how tags tie into this by providing a flexible way to organize and attribute costs across projects and teams. Tags are one of the simplest but most powerful tools for organization and cost attribution in Azure. A tag is a key value pair that you attach to resources or resource groups. Common tag keys include environment, prod, test, dev, cost center, department, owner, application, or project. Values can be whatever makes sense to your organization. By applying tags consistently, you unlock several benefits. In cost management, you can group and filter spending by tag. For example, see all costs where project equals CRM or department equals marketing. This makes it easy to allocate cloud costs to the right budget owners. In governance, you can use Azure policy to require certain tags on new resources, or to add default tags automatically. This enforces good tagging hygiene across teams. In automation, scripts and tools can read tags to decide what to do. For example, a script might shut down VMs at night where environment equals dev, but never touch environment equals prod. In operation, tags help you quickly identify what a resource belongs to and who to contact if something goes wrong. Designing a good tagging strategy up front is crucial. Keep it simple but meaningful. Document standard tags and allowed values, and make sure everyone understands why they matter. For AZ-900, remember, tags do not provide security isolation or technical boundaries. They're purely metadata for organization, reporting, and automation. Next, we'll move beyond cost and organization into data governance by looking at how Microsoft Purview helps discover, classify, and control data across your estate. Data is often a company's most valuable asset, and Microsoft Purview exists to help you discover, classify, and govern that data across on-premises, Azure, and even other clouds. Purview can scan a wide range of data sources, databases, data lakes, file systems, SaaS applications, and build a unified data map. This map becomes a central catalog where you can search for datasets, see where they live, and understand how they're used. A key feature is data classification. Purview uses built-in and custom classifiers to detect sensitive information like credit card numbers, national IDs, or health data. It can then label these assets so you know where sensitive data resides. Purview also tracks data lineage, the flow of data from one system to another. This helps you visualize pipelines and transformations, where data originates, how it's processed, and where it ends up. Lineage is extremely useful for impact analysis when something changes upstream. From a governance perspective, Purview provides capabilities for access governance and supports organizations trying to comply with regulations such as GDPR or HIPAA. You gain better visibility into who can access what data and whether that aligns with policy. The essence for AZ-900, Purview is about data governance and cataloging, not just raw storage. It sits above your data estate and answers questions like, what data do we have? Where is it? How sensitive is it? How does it move? Next, we'll return to broader governance of resources and configurations by exploring Azure policy, which enforces rules on how your Azure environment is built and used. Azure policy is one of the core tools for governing Azure at scale. Think of it as a way to encode your organization's rules into the platform itself, so resources are automatically checked and, in many cases, remediated. At the heart of Azure policy are policy definitions. A definition describes a rule, such as only allow resources in specific regions, require certain tags on all resources, deny unencrypted storage accounts. You can use built-in policy definitions provided by Microsoft or create custom policies to match your own standards. Policies become powerful when you group them into initiatives. An initiative is a collection of policy definitions that address a particular scenario. For example, PCI DSS compliance baseline, or tagging enforcement for all production resources. Both policies and initiatives are assigned at a particular scope: management group, subscription, resource group, or an individual resource. The scope determines where the rules apply, and assignments inherit down the hierarchy. Azure policy evaluates resources for compliance and shows results in a dashboard. You can see which resources are compliant, which are non-compliant, and why. And for certain policies, you can enable remediation tasks that are automatically bring non-compliant resources back into line, such as adding missing tags or enabling encryption. In exam scenarios, Azure policy is the right answer when you see requirements like enforce, ensure all, or stop people from creating resources that. Next, we'll add another layer of safety by looking at resource locks, which protect critical resources from accidental modification or deletion. Resource locks provide a last line of defense against accidental changes or deletions, especially for critical production resources. Locks are applied at different scopes: subscription, resource group, or individual resource. Once a lock is in place, it impacts everything at that scope and below. There are two main lock types: cannot delete. Authorized users can read and modify the resource, but they cannot delete it unless they remove the lock. And read only. Authorized users can read the resource, but cannot modify or delete it. These locks are extremely useful for protecting key infrastructure components, such as production databases, core virtual networks, gateways, or shared storage accounts. Even if someone has the necessary role to delete those resources, the lock will block the action until it's explicitly removed. Because locks can be applied at higher scopes, you can protect entire resource groups or subscriptions. For example, applying a cannot delete lock on a production resource group ensures that the entire environment cannot be accidentally removed. It's important to remember that locks do not replace RBAC or policy. They complement them. RBAC controls who can do what. Policy controls what configurations are allowed. Locks provide a blunt but effective tool. No changes here unless you remove me first. For AZ-900, if a question mentions preventing accidental deletion or tampering of important resources, resource locks are usually the correct choice. Next up, we'll shift from governance tools to the day-to-day management experience, starting with the Azure portal. The Azure portal is often the first place people encounter Azure. It's a web-based graphical interface where you can create, view, and manage almost every Azure resource. When you sign in, you land on a customizable dashboard. You can pin tiles, charts, and shortcuts for quick access to the resources and metrics you care about most. This helps you build a personal mission control view for your role. Navigation is based on blades and panes. Clicking a resource opens a blade with configuration options, metrics, access controls, and related tools. Wizards guide you through creating complex resources like virtual networks or Kubernetes clusters. The portal integrates with many other services. You can open Cloud Shell directly from the top bar, jump into advisor recommendations, view Azure Monitor charts, or check cost management without leaving the browser. From a usability standpoint, the portal is great for learning how services are structured, performing one-off tasks, exploring new features, quickly diagnosing issues with built-in metrics and logs. However, for large-scale or repeatable operations, you'll usually complement the portal with automation tools. For AZ-900, you need to know that the Azure portal is the primary visual management plane, and that there are alternative tools like CLI and PowerShell for scripting. Next, we'll look at those alternatives, Azure CLI, Azure PowerShell, and Cloud Shell, and see how they enable consistent, scriptable management from anywhere. Command line tools are essential for automation, repeatability, and DevOps practices in Azure. Azure CLI is a cross-platform command line tool that works on Windows, Mac OS, and Linux. It uses a simple, consistent syntax, AZ, group, command, and is ideal for scripting in Bash, Python, or other environments. Many cloud engineers use Azure CLI to script deployments, manage resources, and integrate with CI/CD pipelines. Azure PowerShell provides a set of PowerShell commandlets for Azure management. It's especially popular among Windows admins and people already comfortable with PowerShell scripting. The object-based nature of PowerShell makes it powerful for complex automation scenarios. Azure Cloud Shell brings these tools to the browser. It's an interactive shell environment you can launch from the Azure portal, with both basic CLI and PowerShell options. Cloud Shell comes pre-authenticated to your subscription and includes many tools pre-installed. It stores persistent files in a connected storage account. The advantage of Cloud Shell include no need to install anything locally, consistent environment from any machine, quick access while you're already in the portal. For AZ-900, remember, portal, visual management, CLI and PowerShell, scriptable, automatable management, Cloud Shell, browser-based command line with everything ready to go. Next, we'll move from how you run commands to how you define entire environments as code, using infrastructure as code and ARM templates. Infrastructure as code, IAC, is a key modern practice where you describe infrastructure in files instead of clicking through GUIs. This brings the benefits of software development, version control, repeatability, code review to your infrastructure. In Azure, the foundational IAC technology is the Azure Resource Manager, ARM. ARM templates are JSON files that describe the resources you want: virtual networks, VMs, storage accounts, app services, and their configurations. An ARM template typically includes a schema and content version, a or parameters section so you can reuse the template across environments, different names or sizes, a variables section to simplify repetition, a resources section where you define actual Azure resources, optional outputs that return values, like connection strings after deployment. You deploy ARM templates through the portal, CLI, PowerShell, or DevOps pipelines. ARM then ensures resources are created or updated to match the desired state. On top of raw ARM JSON, Microsoft introduced Bicep, a more concise DSL that compiles down to ARM templates, and many organizations also use Terraform to manage Azure alongside other clouds. The big benefit is consistency. The same template can deploy identical environments for dev, test, and production, reducing human error and configuration drift. For AZ-900, you just need to remember that ARM templates and IAC are about declarative, repeatable deployment of resources, not one-off manual creation. Next, we'll move beyond a single cloud and see how Azure Arc lets you extend Azure's control plane to on-premises and other cloud environments. Hybrid and multi-cloud environments are now the norm, not the exception. Azure Arc is Microsoft's answer to managing resources wherever they live, on-premises, at the edge, or in other public clouds. With Azure Arc, you can project non-Azure resources into Azure control plane. For example, you can connect a physical or virtual server running in your data center or another cloud, and it will appear in the Azure portal almost like a native resource. Supported resource types include servers, Windows and Linux, Kubernetes clusters, including AKS, on-prem, or other cloud K8s, databases like SQL, Server, and PostgreSQL in Arc-enabled forms. Once resources are Arc-enabled, you can apply Azure policy, tags, and RBAC to them, and you can collect logs and metrics into Azure Monitor. This brings consistent governance and observability across the entire estate. For Kubernetes clusters, Azure Arc can help you deploy applications and configurations at scale using GitOps patterns. The big picture is that Azure Arc extends Azure's management, security, and governance capabilities beyond the boundaries of Azure data centers. For the AZ-900, remember that Arc is about hybrid and multi-cloud management, enabling Azure-style governance for resources outside Azure. Next, we'll turn to a tool that helps you continuously fine-tune your environment, Azure Advisor, which provides best practice recommendations. Azure Advisor is like a built-in consultant that continuously analyzes your resources and suggests ways to improve them. Advisor focuses on several key areas. Cost. Identify underutilized or idle resources. Suggest right sizing and reservations. Reliability. Recommend high availability configurations, backup strategies, and redundancy improvements. Security. Surface some security-related issues, integrated with Defender for Cloud. Performance. Suggest changes to improve responsiveness and throughput. Operational excellence. Highlight configuration or design improvements. Advisor uses telemetry and configuration data to generate actionable recommendations. For example, it might say, "This VM is consistently under 10% CPU. Consider a smaller size." Or enable backup on this critical VM. Recommendations are presented in the portal with an impact rating and an estimated cost impact, helping you prioritize. You can also export the recommendations or integrate them into workflows. Unlike Azure Policy, which enforces rules, Advisor is advisory. It doesn't block deployments, it simply points out ways to align with best practices. In exam scenarios, if you see a question about optimizing cost, performance, or reliability based on existing resources, Azure Advisor is often the right answer. Next, we'll look at how you stay informed about service issues and planned maintenance using Azure Service Health and Status tools. Knowing when something is wrong, whether globally in Azure or locally in your subscription, is critical. This is where Azure Service Health comes in. Service Health gives you a personalized view of Azure service issues that affect your resources. It tracks three main types of events: service issues, problems in Azure services, like outages or degradations in a particular region; planned maintenance, upcoming changes that might affect availability or performance; health advisories, information about changes, depreciations, or actions you may need to take. You can set up alerts to be notified via email, SMS, or other channels when incidents impact your subscriptions or regions. This helps your operations team respond quickly and keep stakeholders informed. Service Health is different from the public status page, which shows high-level information about Azure's overall status. Service Health is tailored to your environment, showing incidents relevant to the services and regions you actually use. There's also Resource Health, which gives a status view for individual resources: healthy, degraded, unavailable, or unknown. It helps you determine whether an issue is due to Azure or something in your configuration. For the AZ-900, remember, Service Health is your personalized feed of Azure service incidents and maintenance. status page, public, high-level overview, resource health, per resource status. Next, we'll move into monitoring and observability, starting with Azure Monitor and Application Insights, which collect metrics and telemetry from your applications and infrastructure. Azure Monitor is the central platform for collecting, analyzing, and acting on telemetry from your Azure and hybrid environments. At a high level, Azure Monitor deals with two main types of data: metrics, numerical values measured over time, such as CPU usage, memory, request count, or latency. Metrics are ideal for real-time dashboards and alerts. And logs, detailed records of events, traces, and diagnostic information. Logs are stored in log analytics workspaces and queried with Kusto Query Language, KQL. Application Insights is a feature of Azure Monitor specifically focused on application performance monitoring, APM. It instruments your applications, often via SDKs or auto detection, and collects telemetry like request rates, response times, failures, dependencies, and user behavior. Using Application Insights, you can detect performance issues before users complain, trace how a request flows through different components, see which features users actually engage with. Azure Monitor allows you to create dashboards, charts, and alerts. Alerts can trigger actions such as sending emails, calling webhooks, invoking Azure functions, or integrating with ITSM tools. The key exam idea is Azure Monitor and Application Insights give you end-to-end visibility across infrastructure and applications, enabling proactive operations and troubleshooting. Next, we'll zoom in on the log side of monitoring by looking at log analytics workspaces and diagnostic settings, which control where log data goes and how it's queried. Log Analytics is the log engine behind many Azure monitoring features. Understanding how it works will help you reason about diagnostics and investigations. A log analytics workspace is a central store for log data for various sources: Azure resources, operating systems, applications, and even custom sources. Data in the workspace is organized into tables, and you query it using Kusto Query Language, KQL. Diagnostic settings determine which logs and metrics are sent from a resource and where they go. For many services, you can configure diagnostic settings to send data to a log analytics workspace for querying and alerting, a storage account for long-term archival, an event hub for integration with external systems or SIEM tools. Examples of log types include activity logs, resource-specific logs like SQL audit logs, and platform metrics. Configuring diagnostic settings appropriately is key to having the data you need when something goes wrong. You also control retention policies in the workspace. How long data is kept before being purged. Longer retention provides more history but costs more. In an investigation scenario, you might use KQL queries to answer questions like, which IP addresses access this resource? How many failed requests occurred in the last hour? What were the top errors by frequency? For AZ-900, you don't need to write KQL, but you should know that log analytics plus diagnostic settings are how Azure captures and centralizes logs for analysis. Next, we'll shift to availability from a contractual point of view by exploring Azure Surface Level Agreements, SLAs, and what those percentages really mean. Service Level Agreements, SLAs, define Microsoft's uptime commitments for Azure services. They're a critical piece of the reliability story, especially for business stakeholders. An SLA typically states an availability percentage over a billing month. For example, a service might have an SLA of 99.9% availability. This means the service is guaranteed to be up and functioning correctly for 99.9% of the time in that month. Each percentage maps to a certain amount of allowable downtime. For instance, 99.9 allows roughly 43.8 minutes of downtime per month. As the SLA increases to 99.95, 99.99, and beyond, the allowed downtime shrinks. SLAs often require you to follow specific configuration guidelines. For example, you might only get the stated SLA if you deploy across availability zones or use at least 2 instances in a load balance set. If the service fails to meet its SLA, Microsoft may give service credits on your bill. These credits compensate for downtime but don't cover indirect business losses. The exact credit percentage depends on how far actual availability fall below the target. Not all services have SLAs. For example, preview features might be explicitly excluded or carry no formal SLA. For AZ-900, remember that SLAs are per service, sometimes per SKU or configuration. Expressed as an availability percentage. Often influence architecture choices to meet business requirements. Next, we'll build on this by seeing how multiple SLAs combine into a composite SLA for end-to-end solutions. Real-world solutions are made up of multiple components: web apps, databases, storage, queues, and each may have its own SLA. When combined, these form a composite SLA for the entire solution. When components are arranged in series, meaning the system depends on each component being available, the overall availability is the product of their availabilities. For example, if a web app has 99.9% SLA and the database also has a 99.9% SLA, the combined availability is 0.999 times 0.999, which gives you 99.8%. This means that adding dependencies usually reduces overall availability, even if each individual service has a high SLA. It's an important exam insight. The composite SLA is often lower than any single component. Architects can improve composite SLAs by introducing redundancy. For example, using active-active deployments across regions or using multiple instances of a component. Some patterns let you treat components as parallel paths, which can increase overall availability compared to a single path. In AZ-900, you won't be asked to do complex math, but you should understand the concepts: single component SLA equals that component's availability. Multiple dependent components equals multiple SLAs turns into lower composite availability. Redundancy in design patterns can improve the effective SLA. Next, we'll explore Azure Blueprints, a way to package governance and environment setup for consistent deployment at scale. Azure Blueprints were designed to package and deploy sets of governance artifacts, like policies, role assignments, and ARM templates, as a single versioned entity. A blueprint contains artifacts such as policy assignments, enforcing rules across resources; role assignments, granting specific permissions; ARM templates, deploying infrastructure components; resource group definitions, creating consistent layout patterns. By applying a blueprint to a subscription or management group, you can create a fully governed environment in one go. This is particularly useful for establishing landing zones, standardized, secure starting points for new projects or teams. Blueprints support versioning, so you can update them over time and track which subscriptions are using which version. This makes it easier to evolve your governance model while keeping environments aligned. Although Microsoft is increasingly encouraging the use of ARM bicep templates and policy directly, the concept of blueprints is still helpful for AZ-900. It represents governance as code and environment standardization. Think of a blueprint like a company starter kit. When a new office opens, you don't reinvent everything. You roll out the same wiring, security rules, and equipment based on pre-approved design. Next, we'll circle back to security and see how Microsoft Defender for Cloud provides advanced features for threat protection and posture management. Microsoft Defender for Cloud is a cloud security posture management (CSPM) and workload protection solution that sits on top of your Azure and even multi-cloud environment. One central feature is the Secure Score, a numerical representation of your overall security posture. Defender for Cloud analyzes your resource and configurations, then suggests recommendations such as enabling MFA, closing unnecessary ports, or turning on encryption. Implementing recommendation increases your secure score. Defender for Cloud also provides threat protection. It uses signals from logs, network traffic, and behavior analytics to detect suspicious activities, such as brute force login attempts, abnormal process execution, or data exfiltration patterns. When it detects something unusual, it raises security alerts that you can investigate. Workload protection plans add deeper monitoring for specific resource types, like virtual machines, SQL databases, containers, and storage accounts. For example, you can enable just-in-time VM access, which locks down management ports and only opens them briefly when explicitly requested. Multi-cloud support also allows you to onboard resources from AWS and GCP, giving you a unified view of security posture across different clouds. For the exam, the key ideas are: Defenders for Cloud equals security recommendations plus threat detection. Provides a secure score and actionable guidance. Integrates with policies and alerts to strengthen Azure security. Next, we'll close the learning journey with exam preparation tips and a final review, and then we'll use quick review slides as a rapid recap of the entire syllabus. Preparation for the AZ-900 is not about memorizing every Azure service. It's about having confident understanding of the fundamentals and being able to map scenarios to the right concepts. Start with the official Microsoft Learn AZ-900 learning path. It's free, structured around the actual skills measured, and contains hands-on labs that make ideas stick. Pair that with a concise notes deck, like the slides and scripts you're using now, after each module. Cloud concepts, architecture, management, governance. Ask yourself, could I explain this topic to a friend in simple language? Could I recognize which service fits a given scenario? Next, practice with sample questions. Don't fixate on your score at first. Use them to identify weak spots. When you miss a question on, say, ExpressRoute or Azure policy, go back and re-watch or reread that part. During revision, try active recall. Hide the bullets on a slide. Look only at the title, example being Azure policy, and speak for 30 to 60 seconds on what it is, why it's used, and one example. This is far more effective than passively rereading. On exam day, read questions slowly and watch for keywords: governance, private connection, serverless, consumption-based. Use elimination, removing obviously wrong answers, then choose the best remaining one. And above all, stay calm. AZ-900 is meant to be accessible. To lock everything in, the next 3 slides are quick review summaries of cloud concepts, architecture and services, and management and governance. Use them like a final checklist before you sit for the exam. Cloud computing is fundamentally about delivering IT resources over the internet on demand, instead of owning hardware. You rent compute, storage, and services from providers like Azure. Remember the key benefits: availability, designed for minimal downtime using redundancy; scalability and elasticity, handling changing loads by adding or removing resources; reliability, consistent behavior over time, supported by backups and DR; security and governance, centralized identity, policies, and compliance; manageability, unified portals, automation tools, and monitoring. You've seen the main deployment models. Public cloud, which is shared provider infrastructure, great for agility and global reach. Private cloud, dedicated environment for one organization, gives you more control. Hybrid, mix of on-prem and cloud, often used during migration. You've also reviewed the service models: IaaS, infrastructure as a service; VMs, storage, networks, maximum control; PaaS, platform as a service; managed platforms like App Service, which focus on code; SaaS, software as a service, complete applications like Microsoft 365. You just use the software. Pricing is largely consumption-based, with options like pay-as-you-go, reservations, and spot instances. Serverless extends this, charging only when code runs. Finally, never forget the shared responsibility model. Azure secures the infrastructure of the cloud. You secure your data, identities, and configurations in the cloud. Next, we'll quickly recap the big ideas from Azure architecture and core services, so these building blocks are fresh in your mind. Azure's global architecture is built on regions, region pairs, and availability zones across many data centers, all connected by Microsoft's private backbone network. You choose regions for latency, compliance, and redundancy. Your compute options include virtual machines for full control, app service for managed web apps and APIs, Azure Functions for serverless event-driven workloads, containers and AKS for orchestrated microservices, Azure Virtual Desktop for hosted desktops. Networking revolves around virtual networks, subnets, NSGs, and VNet peering. For hybrid connectivity, you pick between VPN gateway, encrypted over the internet, and ExpressRoute, private dedicated connection. You also decide between public endpoints, service endpoints, and private endpoints for PaaS services. Storage choices are blob, files, queues, tables, and disks, combined with access tiers, hot, cool, archive, and redundancy options, LRS, ZRS, GRS, RA-GRS. Identity and access rely on Microsoft Entra ID, with supporting concepts like hybrid identity, external identities, RBAC, role-based access control, conditional access, and zero trust. If you can look at a scenario and quickly say, this needs ExpressRoute, not VPN, or this is a PaaS app on an app service, not IaaS VMs, you're thinking at the right level for AZ-900. Next, we'll do one final quick review of management, governance, monitoring, and exam mindset. And then, you're ready to tackle practice questions, and then the real exam. Management and governance in Azure starts with cost management and billing, tags, and the pricing calculator. You estimate beforehand, then track and optimize spending afterwards. For governance, key tools are tags for organization and cost allocation, Azure Policy to enforce rules and configurations, resource locks to prevent accidental deletion or changes, management groups and subscriptions to structure environments, Microsoft Purview for data governance, blueprints, conceptually, for standardized, governed environments. Monitoring and operations rely on Azure Monitor, metrics and alerts for visibility, log analytics and diagnostic settings for logs, application insights for app telemetry, service health and resource health to understand outages, advisor and defender for cloud to improve cost, reliability, and security. SLAs tell you what availability level Azure commits to, and composite SLAs remind you that multiple dependencies usually reduce overall availability unless you design for redundancy. For the exam itself, focus on conceptual understanding, not memorizing every SKU. Practice mapping scenarios to services and features. Use active recall and spaced revision with these slides. During questions, read carefully, look for keywords, and eliminate obviously wrong options. With all this in place, cloud concepts, architecture, services, governance, security, monitoring, you're well prepared to pass the AZ-900 and, more importantly, to have a strong mental model of Azure for future learning. Don't forget to like, share, and subscribe to Knowledge Catch for more tech videos. Thanks for watching.